propagation. So since you need to compute the gradients with respect to the weights in each layer, so assume that the input in this unit is the input and the corresponding weight. So you multiply these two and sum them up. Then you, when do backprop, you have to compute the gradients with respect to the weight of this unit, so you can update the weights, and also you have to compute it with respect to the input so that you can apply the chain rule with respect to the previous layers. So yeah, you have to compute two gradients for the input and for the weight, so the computational cost is about twice as the forward pass. Okay, and yeah, we apply the forward pass and the backward pass in alternative steps in order to train our neural network. Okay, so now assuming that we want to apply these standard neural networks on images, if we consider an image with about 200 and 200, 200 by 200 pixels, and with around 400 hidden units, so this is the number of actually the number of weights that we want to train. Yeah, we get the parameters are the weights we want to train. We get a very large number, so it's almost 2 billion parameters. So in standard fully connected networks, there is a lot of computation involved, and it's not really efficient for images. So yeah, there is a lot of waste in terms of resources, and also in order to train these layers, we would need a lot of training samples which are not available. So we need to consider a different model based on the observation that there is some spatial correlation that is only local. So so for example, what we want to do is to replace these units with some layers that are locally connected. So instead of having weights with respect to the entire image, we just have weights to some local parts of the image, and then these units will be able to learn some features, some discriminative features from the input image. Okay, so yeah, this would work. So this is the first idea of moving towards convolutional networks. So the first idea is to apply these units locally, not globally. And yeah, the idea is good. It reduces the number of parameters. So now we have only 4 million parameters to learn. The problem is still that well, in natural images, these are not perfectly aligned. So the object is not always in the center. So this, for example, this setting would work well for face recognition, where the face is usually aligned prior to auto applying the recognition model. But in practice, yeah, the objects are not perfectly aligned in the image. So then what we want to apply is that we apply these units not in a single location, but we apply it in every location over the input image. So this is a stationary assumption. So the statistics, we assume that the statistics are similar at different locations. Yeah, so for example, a face, in this case, a face can shift everywhere in the image. So then we can just apply the same filter in every location, the same unit in every location. So the base idea is that each time we apply this layer in a different location, we always use the same weights. So we start, for example, with from this corner, and we apply the unit in every location to try to extract some meaningful patterns from the image. but we always use the same parameters. So in this way, the convolutions will learn some kernels or some filters. So usually we call this unit a kernel or a convolutional filter. So yeah, the main idea is that the filter that we learn activates or has the maximum activation where the image correlates well with the filter. So if we go to a very simple case, the one-dimensional case, and we pass this filter represented by the function g in red. So we pass it over a one-dimensional signal from left to right, and we just apply the convolution operation, which is multiplying the filter. So these are the filter, remember, it contains the weights of a neural unit. So actually the weights are the filter itself. So yeah, these weights, when are multiplied with the input, we obtain a very high response when the input has the same shape as the filter. So in this case, we have a square filter, and when we apply it over the signal on top, we obtain the maximum activation when the filter is right on top of this signal, on the blue signal. And if applied on a different signal, we will see that the activation, so the activation is the function resulted after the convolution, which is depicted in black. So you will see that this function has the highest response here in this point, and here it has the highest response when the blue shape has about the same shape as the filter. So it's somewhere around here. Okay, so this is the convolution operation in 1D. If we go to the 2D, so we want to apply it on, for example, on images. So we have our convolutional filter here. We apply it over this region of the image, and we obtain an output. So the outputs that we obtain in this matrix here will be correlated. Will have high values when the filter is well correlated to the input image. So for example, if the filter contains, I don't know, a vertical bar, we will have a high response here when the image contains a vertical bar. So we apply this filter in every location, and we should obtain a map with high responses when the filter correlates with the image. So I think we can see this in this very simple example where we have a filter that activates on vertical gradients. So this is a standard filter that can be applied, for example, on the image. So this is the pictogram of this filter, and we apply it when we apply it on this input image, we obtain this response. So we can see that we have high responses when the image is well correlated with the filter that looks like this. Okay, so usually where we have vertical bars, we have high responses. And when we have I don't know, so for example here we have some fog, so there are no vertical gradients here, so this gives us a low response. Okay, so yeah, usually the activation, so the result of the convolution operation is an image that contains high responses when the input image looks like the filter, and low responses when the image doesn't look like the filter that we apply. Okay, so the only difference here is that instead of applying, so in convolutional layers, we do not put the components of the filter by hand, but we learn them in an end-to-end fashion way. Okay, so yeah, we discussed about applying one filter on top of the image. So what I said previously is that we want to have different units that learn different patterns. So one convolutional layer typically contains multiple filters. So for example, if we have um, and this configuration 100 filters, and each having a spatial support of 10 by 10, then the number of parameters that we get is around 10k. So this is because we apply the same filters in every location. So the number of parameters, or the number of weights, is 10 by 10, 100, and we have 100 filters, so 100 times 100 is 10k. So this significantly reduces the number of weights that we need to learn in a neural network layer. So the main difference, so remember that we started with 4 billion parameters with when we had fully connected layers, and now with a convolutional layer we only have 10,000 parameters. So it's a significant reduction in the number of parameters. So yeah, this is one key aspect, is the efficiency of the convolutional layer. Okay, so yeah, with this idea that you can use convolutional layers, the first architectures that appeared with this kind of layers contained 3 or 4 convolutional layers. So besides the convolution, we also have subsampling layer, or pooling layers, that we will discuss a bit later. Okay, so yeah, a few more things about the convolutional layer. So usually we apply ReLU activation, which is the function maximum of 0 and the result of the convolution operation. So then here in the convolution we have some input feature map and the kernel that applies on the input feature maps. So in the end we take as input some feature maps, we pass them through the convolutional layers, and we obtain some output feature maps. And these are provided as input to the next layer, and so on. So one important aspect here is that when we apply a filter on top of the input feature maps, we apply it on all the input feature maps. So imagine that these input feature maps are actually filter responses from a previous layer. And now when we apply a filter, so in the filter has a spatial support, but the depth of the filter is always the same as the number of input feature maps. So we apply the filter on top of all of these, and we obtain a single feature map from that. So for another filter, we apply a different feature map, and so on. So usually the number of feature maps of the output feature maps is equal to the number of filters in the convolutional layer. So this is one thing to remember. And the other thing is that the filters always apply on all the activations from the previous layer. So in this way, the filters also learn to combine the filter responses from the input layers. So this means that, for example, the filter on the current layer, for example, can learn to combine, I don't know, an activation of a straight vertical line with an activation of a straight horizontal line to produce a filter that responds to corners, for example, or so on. So these can get into more and more complex combinations, and you will see some examples later in the course. Okay, so we have some questions that we want to answer. So I will come back to these questions and let you give an answer. But first, I want to to introduce some aspects and to specify the parameters and all the computations that are involved before trying to answer this question. Okay, so yeah, an activation map, its size depends on the input. So we have an activation map here as input with 32 by 32, and we have 3 activation maps. So this is the number of activation maps, and we apply a filter of 5 by 5 by 3. So if we apply this filter on every location, as shown in the previous slides, so we apply it on every location on these input activation maps, we will soon figure out that we can apply the filters in only 28 locations. So let's look at a smaller example. So we have an input image with 7 by 7 pixels and a filter of size 3 by 3. So when we apply this filter on top of this image, we can apply it 5 times. So we obtain an output of 5 by 5. And we can also actually apply the filters not at every possible location, but we can also use a stride. So the stride means that we jump with a fixed number of pixels. So stride 2 means that we jump over 2 pixels. So then we apply the filter here, we jump 2, we apply it here, we jump 2, and we apply it here. So in this case, the output will be 3 by 3. So this is one parameter that comes into question. And sometimes you have to figure out how to fix this parameter. So in many cases, in many frameworks, if the stride is not consistent with the input, it might give you an error, or the result might not be predictable. So for example, you can apply the filter here, and you can also apply it here, but then here you will not be able to apply the filter because you have no components on this part. So if you just try to apply the filter like that, it will not be possible because it doesn't fit exactly. So the formula to compute the size of the activation map based on the previous examples is you take the size of the input image, you subtract the size of the filter, you divide it by the stride, and you add 1. So when you had the stride 1, and when we replace the size of the image and the size of the filter, we obtain the size of the output, which is 5. Then for stride 2, we obtain the size 3. And for stride 3, we can see that this number is not a round number. So this is why it is not possible to use a stride 3 in this case. Yeah, well, there is one note here that we can add padding to the input image in order to be able to use the desired stride. So yeah, this equation doesn't take into account the padding that we can add to the input image. Okay, so yeah, if we apply, so about the padding, another motivation for using padding is that when we apply the convolution, for example, with 5 by 5 filters repeatedly on an input image of size, let's say size 32 by 32, then the volume will gradually reduce from 32 to 28 to 24 and so on. So yeah, if you reduce the spatial dimension too soon, you will not be able to use very deep neural models. So you will have a limitation in terms of the number of filters that you can use in your network. So in order to avoid this limitation and to have a better control on the spatial reduction, we use zero padding on the input, which also allows us to use the stride that we want. So yeah, going back to the previous example, so if we add, for example, if we want to keep the input size, um, we can add just a stride of 1. So in this case, the activation will be the same size as the input. So the output will be 7 by 7 in this case. Yeah, and in general, if we want to keep the dimension of the input, so if we want the output to have the same size as the input, we just have to use a padding that is equal to the size of the filter minus 1 divided by 2. So in case of 3 by 3 filters, this is 3 minus 1 divided by 2 is equal to 1. So this is why when we add a padding of 1 around the entire image, we obtain an output of the same size as the input. Okay, yeah, so this rule applies when the stride is 1. Of course, if you increase the stride and you still want to keep the dimension of the input, then you have to use different padding, but this would not make too much sense. So preferably if you want to keep the input size, just use stride 1 and add the corresponding padding using this formula. Okay, so yeah, what about the output volume? So now we discussed about the input and the size of the activation map. But as I said, for each filter, we can obtain a different activation map. So in the end, the output volume, the depth of the output volume depends on the number of filters. So suppose that for a convolutional layer, we have 10 filters with with stride 1 and padding 2, and the filters have a spatial support of 5 by 5. So yeah, what do you think will be the size of the output volume in this specific case? So yeah, I'm waiting for this question. I'm waiting for an answer from you guys. Yeah, so look again. So these have stride 1, padding 2, filters are 5 by 5. So Mihai, that's not the right answer. So yeah, I know that the MacBook is trying to stream the higher quality video, so it's a trade-off between the MacBook taking off and the quality of the video. So I'm sorry about it. You can, if you can let me know if you prefer to have lower quality video than hearing these sounds. We can go back to that. Okay, so yeah, we have a good answer. It's 32 by 32 by 10. So that's the output volume. So yeah, Alexandra got the right answer. So yeah, the input volume. So going back to the example, since we're using, I think the main point here is that the padding is 2. So when we use padding 2, it means that the size of the output volume will be the same as the input volume. So it will be 32 by 32, so the same spatial size. And we have 10 filters, so the output volume will be 32 by 32 by 10. Okay, so the next question is, what is the number of parameters of this layer? So yeah, we managed to figure out the number of the size of the output tensors, but what is the number of parameters? What are the number of weights that I'll learn in this layer? And please also take into account the bias terms. So those are also learnable weights. I didn't discuss about them so far, but yeah, the filters also have a bias term. Yeah, so I'm going back on this slide, so I'm not sure which slide I should go back. Yeah, perhaps that's maybe related to the first question. So I'm staying here and just waiting, trying to pick for an answer. So let's keep it like that. Yeah, so that's not the right answer from Mihai. So now the question is the number of weights. So we have the number of the size of the output volume. Now we're asking about the number of weights. So recall that the weights are the parameters that are learned for the convolutional filters, right? Okay, so we have, let's say, a close answer. From John, if that's your actual name. But it's still not complete. Okay, so we have a good answer again from Alexandra. Yeah, so the total number of parameters is 760. So this is because the filters have a spatial support of 5 by 5. So John was almost right on the answer, but he forgot that the filters apply on the entire input volume. So the filters are actually three-dimensional and have 5 by 5 by 3 components. So one filter has about 75 weights plus the bias, so 76. And then we have 10 of these filters, so the total number of parameters is 760. So yeah, we have a good answer again from Alexandra. So now I asked you for some specific answers for this example, but in general, so the size of the output is equal to n, which is the number of filters, and the spatial dimension depends on the size of the input volume and the size of the filters. Of course, we are also assuming here that the stride is 1 and we have no padding, so this formula will be slightly different. And also the number of parameters, so we have the filters are k by k by m, and also we have n of these filters, so this is the number of coefficients that need to be learned. So here actually it's m times k plus 1 from the bias, then we have times n. Probably we should remember that. Okay, so what's the computational cost? So we have these filters that we apply on every location on the image. So we just multiply the kernels that we apply in every location. So every location. So actually for every output in the output volume, we obtain an output. So the total computational cost is equal to this large product. Okay, so yeah, a lot of components to consider here from the convolutional layer when we discuss about the cost. So, but still remember that this is more efficient than fully connected layers. Okay, and yeah, we discussed about previously about the feature maps and yeah, I'm not sure. so yeah, we discussed already about this, but so in the end, the size of the filter is equal to the spatial support, and also taking into account in the third dimension the number of input features. So yeah, the size of the number of activation maps is equal to the number of filters. So this is straightforward. Okay, so the main idea is that usually, so I think what I'm trying to say in these slides is that when we go deeper into the network, we usually add more filters, and usually the spatial support is decreased. Even when we use zero padding, we can add pooling layer to reduce the spatial support, and this is necessary to ensure robustness to rotations and other translation and other variations. Okay, so usually there are more output feature maps than input feature maps. So this is one observation, and this is because usually we want to increase the filters as we go deeper into the network. Why is this? Usually it's because in the preliminary layer, so this is also related to a later discussion. Yeah, so it's a bit later in the slide, so I'm going to do a short preview here. So in the preliminary layers, we use the networks learn these generic filters like I don't know, lines, corners, edges, and stains. And as you combine these filters into more complex filters, so this combination happens because, for example, the convolutional filters on this layer are applied on top of the entire depth of the activation maps. So you will see the responses from all these filters here in one location, so you can obtain here a more complex filter. So as you learn more complex filters, these also become more specific for certain patterns. Like, for example, they start to recognize, I don't know, parts of objects. So since these become more and more specialized, you also need more filters to recognize more object classes. As opposed to the first layers, which obtain very generic features, they can be applied to almost any object class. So here you will not need so many filters. Okay, but more on this a bit later. And yeah, also the size of the filters have to match the size and scale of the patterns that we want to detect. So this is typically with respect to the task that we want to address, but also it kind of depends also on the depth of the network. So we can still use really small filters and just try to if you want to discover larger patterns, you just add more convolutional layers, and this increases the spatial support. So what I mean here is that, for example, if we apply here a filter of 5 by 5 and the output, so for a 5 by 5 region, you will get an output with a single component here. So then when you apply these filters, they are still 5 by 5, but in their receptive field, in their 5 by 5 receptive field, they will see the output from these 5 by 5 filters. So actually you can imagine that this, for example, this region reduces to one component here, and we have several of these 5 by 5 regions that fit into a 5x5 region in this activation map. So when we apply here a 5x5 filter, it actually corresponds to a larger receptive field in this activation map. So as you add more and more layers, these will correspond to larger and larger parts of the input activation map. So you can, if you cannot train very deep neural networks, perhaps you can increase the size of the filters, but then if you can also train deeper networks, you can just use smaller filters and hope that you can recover this receptive field through the number of layers. Okay, one observation. So in many neural network architectures, you will see convolutions with 1x1 filters. So this makes complete sense because these filters also apply on the entire depth of the input tensor. So in this case, for example, we can, for example, reduce the volume depth-wise from 64 components to 32 by applying 1x1 filters, 1x1 convolutions with 32 filters. So this is one potential application, but it can also be used in different configurations to obtain, for example, separable convolutions. So yeah, this is just an idea to optimize convolutions, for example. So instead of learning 30, let's say that the spatial support that we want is 3x3. So instead of applying filters of 3x3x64, we just apply 2D filters with 3x3 components, and then we apply convolutions with 1x1x64. So it's just decomposing three-dimensional filter into two-dimensional components, one with spatial support and one with depth-wise support, and the number of parameters that you learn are lower, and yeah, it gives you the opportunity to train more efficient networks. So another application of 1x1 convolution is in these neural networks that use separable convolutions. So one application, one example is the mobile net architecture. Okay, so yeah, the key ideas yeah, is to remember that when we apply neural networks to images, it should scale quadratically with respect to the size of the input. So because the input has two dimension, and the solution is to connect each hidden unit to a small patch of the input and share the weights across the spatial dimension of the image. So yeah, the solution is to apply actually the convolutional layer. Okay, so this idea was initially introduced in this paper by Jan LeCun in 1998. So the idea of convolution is very old. And in the same paper, they also introduced the subsampling layer. So one way to make the detector more robust is to apply pooling, the pooling operation. So by pooling, what we mean is we take, for example, the maximum response from a certain region, and if we do this at a different location, we obtain robustness to exact spatial locations of features. So what this means is that we want to obtain a model that is invariant to slight changes of the spatial locations of these features. So yeah, in one pooling layer we obtain this robustness to small variations, but if we have more pooling layers in our convolutional neural networks, we increase the robustness, and this can actually go to almost the entire image in some cases. So yeah, for the pooling layer we have different operations that we can apply. So the most popular one is the max pooling operation, which just takes the maximum from each spatial location that we apply the pooling filter. Another, perhaps the second most popular, is to do average pooling, and then there are different other ways to obtain the response in a certain location. And there are also some new ideas in the literature that use, for example, the standard deviation instead of the average, and so on. So it has really different ways to apply. But I think that the most common one is the max pooling, and it also has a visual interpretation. So imagine that you have this input volume, and in the input volume you have an activation map that looks something like this. So remember that, recall that in the activation map you have high responses, so the white stains correspond to locations where the filter has high responses. And when we do the pooling operation, we just apply these filters on top of the activation map. So for example, here we have 2x2 filters that are applied at the stride 2. So this will reduce the spatial dimension of the input volume from 224 to 112 on each spatial dimension. So when we have a pooling operation, usually the depth stays the same. So we have the depth is 64 and 64 in both input and output. We are just reducing the spatial dimension. So here in each location we keep the maximum. So from this activation map we obtain this activation map. So yeah, here you will see that the image is more pixelated, but this doesn't matter so much. What it matters is that, for example, if we had a high filter response in this region, we want to keep the high response also here. So actually, when we do this, it means, so we have a high filter response. So for this 1 pixel here, we have a correspondence of 2x2 pixels here. So so actually the high response can be anywhere in this 2x2 filter receptive field of the filter. So in this small location, the high response can be anywhere. So this is why we achieve this small invariance to the location of the highest response. Okay, so yeah, this is how the pooling operation works. So now going one more time through the explanation previously indicated. So yeah, so we have a 6 here, which is the maximum, but actually you can imagine that the same output can be obtained if the 6 is on this cell or in this cell and so on. So this means that the high filter response can correspond to any cell in this region, and we have if we have a sequence of pooling layers, this region will grow higher and higher. So because this cell will correspond to a high some region in a previous activation map and so on. Okay, so for the pooling layer, we have some straightforward answer, which are kind of equivalent to to the convolutional layer. So as I explained, for the convolutional layer, the output is also proportional to the size of the input, only that this time usually we apply the kernels with a stride of k. So if the size of the kernel is k, we apply it at a stride k. So then the output volume is the input volume divided by k. And we keep the size, the number of activation maps. So the size is m. We have m activation maps, and their size will be reduced usually by k. And also the computational cost is proportional to the size of the input. So here we do not have any multiplications over the input. And yeah, also the pooling layer has no parameters to learn. Okay, so another question, how do we set the size of the pools? And here it depends how much invariant or robust we want our model to be. So it depends, yeah, the level of invariance that we want to achieve, and also how many pooling layers we have in the network. So if we have a very deep network where we can add a lot of pooling layers, we can just use, I don't know, pooling of 2 by 2. And yeah, one interesting question for you. So as I mentioned previously, for the convolutional layer, it makes complete sense to use 1 by 1 filters. Do you think that for pooling layers it makes sense to use 1 by 1 filters or not? So yeah, I don't have the question written down, so let me repeat it. Do you think that it makes sense to use pooling layers with filters of size 1 by 1? So k, the size of the filters, k is going to be equal to 1. Yeah, so just write the entire answer no, because yeah, so it won't do anything. That's correct. So if you just apply the maximum on a 1 by 1 filter, you will obtain the same activation map as the input, so it doesn't make sense to apply it. Okay, so thank you for the answer, Andrei. So now another interpretation for the pooling layer is that it collapses the learn manifold. So yeah, actually when you apply convolution, the input is reduced to a linear manifold. And actually linear, it means that for different filters you obtain a different linear manifold, and when you combine these linear subspaces, you obtain this linearized manifold. And then when you apply the pooling layer, it collapses this manifold, and it gives you invariance to, I don't know, rotation and other variations in the input. Okay, so yeah, so discussing about the size of the receptive field. So I made this observation a bit earlier. So when you have, for example, a convolution operation, we have, let's say, 3 by 3 filters. So these 3 components go to a single component here, and then when you usually apply a pooling layer after a convolutional layer, and now depends on the size of the pooling layer. So some region of the pooling layer corresponds to a larger receptive field in the input. Okay, so yeah, usually what happens in a convolutional block. So a convolutional block usually contains a few convolutional layers and the pooling operation. So yeah, you learn a filter bank of convolutional filters. You apply ReLU so that you eliminate negative filter responses. So in the visual domain, for example, we are not interested in the negative filter responses. So we want to learn to detect patterns where the filters activate. So where the filters have high responses, and we're not interested in locations where responses for a certain filters are very low. And then we apply the pooling operation to to obtain spatial robustness for these features. Yeah, so some high level of interpretation, we can think that this convolutional block is somewhat similar to SIFT or HOG. The main difference is that the convolutional filters are learned in an end-to-end fashion, so they are not designed or engineered by people, so they can adapt to whatever data you have at the input. Yeah, so going back to the previous discussion, so what I said before is that usually after each stage we increase the number of feature maps and we reduce the spatial resolution, which gives us invariance to spatial translation, rotation, scale, and so on, and also increases the uh, we increase the number of features because we increase the specificity of those features. Okay, so the typical architecture contains these multiple convolutional blocks that are placed one after the other in a sequence, and then at the end we have some fully connected layers and the class labels in order to recognize objects, or I don't know, different things that we want to recognize in the input images. Yeah, so for object recognition, people studied the filters and the input regions that they activate on. And if you look at, for example, from this paper at ICCB 2014, they studied this problem in depth, and they found that the filters in the first layer of neural networks activate on basic patterns like edges of different objects with different orientations, stains of different colors like green, and stains with some contrast, and so on. So this is in the first layer. So then, for example, from these locations, so all these, for example, could be, for example, the first one, the first filter in each, the first output. So this is the output, right? So the first output in corresponding to every feature. So we take this one, this one, this one, and so on. So these will be the filter, the responses of different filters in the same location, suppose. So then we can apply a filter on top of these locations, and we obtain more complex filters. So here these really are 3D filters, but are just represented in a 2D image. And yeah, you can see here in the 2D image, so here we have just edges and stains. So in the second layer, we start to have corners. So if we combine, I don't know, vertical edge and the horizontal edge, we get some corners here, and we see that this filter activates on things that have corners, like corners of a window, I don't know, and so on. So here we also have other combinations. So this is some sort of pattern with horizontal lines, a pattern with curved lines here with a certain orientation. Um, this one seems to activate on holes or things that look like holes, like eyes and so on. Yeah, so we see that the patterns here are more complex, and these are formed actually by combining the filter responses from the previous layer. We also see bars here and so on. Then if we go to the third layer, we see even more complex patterns that are obtained by combining the patterns from this layer. So imagine that you can, for example, combine this round shape with some straight line, and you get, I don't know, the front wheel of a car. So it has this round shape and this part here. That is actually part of the car, the front door or something. Yeah, and we also have different texture patterns, different object parts. So this is some, I don't know, some object with some green background. We have some bird beaks and heads here. Yeah, so they have some visual correlation, but you can see that they can also activate on things. So these, I think most of them are car wheels, but we also see some high responses in on different images that kind of have the same shape. So yeah, this combine into the fourth layer of the network, where we see even more more complex object parts. So we see here, for example, heads of certain races of dogs, some round shapes like clocks, and I don't know, whatever is here. Yeah, again, bird feet and bird body and so on. Then in the fifth layer we have even more complex body parts and even more bigger body parts. So here, for example, you have the upper body of a person or the upper body of a dog, head of a dog, flowers, and so on, bicycles. Yeah, so the main idea is that as we go deeper into the network, we have activations on larger object parts that are more specific to certain classes. So yeah, so these patterns are very common for all images and for all objects, so you don't need so many filters in the first layer, but as you go deeper, these patterns get more and more specialized to specific object classes, and this is why you need more filters as you go deeper into the network. Okay, so yeah, this ends the first part of our presentation, and we now move to some case studies and try to figure out these the components in these neural architectures. So we start with the first neural network, which is the first that was introduced, the first convolutional neural network that was introduced, which is LeNet. The names come after the first author, Jan LeCun. So it's short for LeCun network. Okay, so in this neural network we have um, 5 layers, and usually we count the convolutions and the fully connected layers. So we have convolution, subsampling, 2 fully connected, and 1 classification layer. Okay, so yeah, in the first layer, for example, we have 6 feature maps, and the spatial support is 28 by 28. So this figure is taken from the paper, and the input is 32 by 32. So in this time they just use stride 1. So when the network was introduced, they didn't thought about using a different stride. So the stride is 1, and they also didn't use padding. So they didn't thought of training very deep neural networks. They didn't need to for their application. But and I think they also didn't have the means then to train so deep neural networks. But anyway, so yeah, the padding is 0 and the stride is 1. So here they actually use filters of 5 by 5. So that's why you get 28 by 28 um, activation maps. Sorry, the size of the activation maps is 28 by 28. Then we have 6 activation maps, which means that we have 6 convolutional filters here. Then we have a pooling operation. So they used, in their original architecture, they used average pooling. And recently we learned that max pooling is actually better to use. And you see that the activation maps go down from 28 by 28 to 14 by 14. So it means that the pooling layers have 2 by 2 filters that are applied at the stride of 2. So they are just, they don't have any overlap. Then they apply again 5 by 5 filters. So they reduce the spatial dimension of the activation maps, and now they used 16 filters. So the output volume is 16 by 10 by 10. Then they apply another subsampling layer and they reduce the spatial dimension of the activation maps to 5 by 5. And then they have 2 fully connected layers and the classification layer. So this is the LeNet architecture, and I think it's straightforward to figure out yeah, all the components and how it works. Okay, going forward to another important architecture. So this was introduced by Krzyzewski in 2012 and was trained on the ImageNet database for the 2012 challenge, object recognition challenge. So yeah, this is a picture from their paper. Some interesting things here is that they, I think this is the first time they managed to train a network on GPUs, but they didn't have enough memory to fit the entire network in a single GPU, so they actually trained 2 independent networks. So this is why we have this representation here. So this part was trained on one GPU, this other part was trained on a different GPU, and then they just concatenated the filters and use it in a single network during inference. So this was their idea to cope with their limited limited GPU memory. Okay, so yeah, we're going to discuss more about memory in the next slide, but here just to figure a few things out. So you can see here that we have, so for the first convolutional layer, we have 48 activation maps here and 48 activation maps here. So we have a total of 96 activation maps. And we can see that the filters have 11 by 11 components. So the filters are quite large, and they adapted their filters in order to learn larger patterns, and they didn't have the computational power to run deeper networks. So these started, or actually the knowledge to run deeper networks with smaller filters. This was discovered in um, more recent architectures like Google Net and ResNet, which we're going to discuss a bit later. So yeah, so they use 11 by 11 filters. So if you try to compute the output volume, so the input images have 227 by 227 pixels, and the images are color. So we have the images are RGB. So anyway, the spatial dimension of the activation maps is 55. So this is obtained by subtracting 11 from the input image. So 11 is the size of the filters. This is the size of the input image. We divide it by the stride and add a 1, and we obtain the size of the activation maps. So here they have the output volume is 55 by 55 by 96. Okay, so one question now for you. So this should be easier following the explanation from above. What is the total number of parameters in this layer? So we have 96 filters with 11 by 11 components. And what is the total number of parameters? You can give me a rough estimation. You don't have to give me the precise number, but just, I don't know, at least a rough estimation. Okay, so I see now. So let's just wait for an answer for this and try to repeat 11. Yeah, so okay, so let's okay, so yeah, none of the answers are completely correct from Mihai and Matei. So yeah, you must combine your answers to give the final answer. So but you're quite close. So yeah, the main idea is that you have to remember, as Matei did, you have to remember that the input size has 3 channels. So you have a depth, the depth is 3, so the output volume is 11 times 11 times 3, and you have 96 filters. So this is roughly 360, and assuming that this is roughly 100, you get around 35k parameters here. So in the first layer they have about 35,000 parameters. Okay, so Yeah, trying to go back to this slide. Yeah, so this is just an interpretation that the pooling layer collapses these linear manifolds into one manifold. So yeah, I think it's just maybe just an imagination exercise. So if you imagine that the conv layer, so for each filter, the input is projected on some linear manifold. So you have these different linear manifolds from different filters, and when you do the pooling operation, you so these can activate for example, if you take this airplane, suppose that you have a filter here that activates on on horizontal on diagonal lines, let's say, that are oriented like this. So we are not thinking about the wings. So if you want to recognize the airplane in a different position, you will need a different filter that's oriented. It's kind of the same filter, but it has a different orientation. So this will be projected. This airplane will be projected to a different manifold. And when you apply the pooling layer, you increase your robustness to the location and to also to the scale if you want, and also to the rotation, so all affine transformations. So then for example, in this example, you kind of project all these linear manifolds into a single manifold, where the same object should reside in the same region of the same filter should go in the same region of the manifold. Yeah, so in this case you have a more you obtain a more general model that is robust to this kind of these variations. Okay, so trying to go back. So we had one more question here. Yeah, so the question now is about, yeah, it's this one. Okay, so we discussed about the convolutional layer. Now we have a max pooling layer. So here you see that they already introduced max pooling. And for the max pooling layer, they have they use 3x3 filters and apply them at a stride of 2. So the stride is the stride is 2, is not equal to the size of the filters. So it's if you want, it's a bit unusual, but what it means is that it reduces the volume. So you have a hint here for the spatial dimension, and of course you can also see the components here. So yeah, it's 27 by 27 by actually, yeah, the answer it's not here. So I'm just waiting for an answer for you. $27, yeah, by 96. So yeah, recall that you keep the number of activation maps from the input, And actually here it's not really well represented in their figure, so they're using max pooling, and they are also representing here the convolutional layer, the next convolutional layer, which contains so another question, what is the number of parameters in the pooling layer? So the number of parameters is 0, as I said before, so no need to answer. So yeah, after the first pooling layer, the spatial dimension becomes 27 by 27 by 96. Then they use 5 by 5 filters, and they have 256 filters of 5 by 5, and so the dimension will be 128 by 128, and the spatial dimension will be 27 by 27 because they add padding of 2. So for the first layer they use padding 0, but now they add padding 2, and then they go down to 3 by 3 filters, and they have another pooling, a normalization layer, convolution, another max pooling, and fully connected layers with 4000 units. And finally, the classification scores for the 1000 object classes in ImageNet. So yeah, this is the first application of rectified linear units in a neural network. They use these normalization layers that normalizes the weights. And now I think the more common idea is to normalize the input using batch normalization. They used data augmentation. So this is an idea. Data augmentation was also used before deep learning. And of course, if you want to train deep neural networks, with they have many parameters, and you have to add a lot of training data to obtain good models. They also used dropout. So dropout is just a technique that cuts down some of the neural units. I discussed more about it last year. So it's just an approach to eliminate some part of the neural architecture. As optimization, for the optimization, they use stochastic gradient descent with momentum using the rate 0.9. They started with a learning rate that is quite high, 10 to the power of -2. So they also reduced the learning rate manually when they observed the validation accuracy reaches plateaus. And yeah, in the end, they trained 7 of these neural networks. So they used an ensemble to improve their performance. So they reduced their top 5 error rate from 18% to 15%. Okay, so and I think that the next year the visual geometry group from Oxford introduced VGGNet, and they mainly took the AlexNet architecture and they just added more layers to their network. They also used only 3 by 3 convolution, so they used smaller convolutions. And they tried to gradually increase the network, the number of layers. So they used 11 layers, 13, 16, and 19. And they obtained better results with the 16-layer VGG network. They observed actually that the 19-layer VGG obtains slightly lower performance, and yeah, if you just use this convolution and pooling blocks, at some point around 20 layers, something like that, your performance will no longer increase, and actually it might even start to decrease. And this is because it is very hard to train such deep models, because the gradients that you backpropagate through the network involve a lot of multiplication operations, and if the gradients are not well scaled, they can easily vanish, so go close to zero, which means that you cannot update the network, or they can explode if they are above unit. When you multiply them, they will reach very high values, and they overflow the floating the bits for floating point numbers, and the gradients explode. So yeah, so they managed to slightly increase the deep of the the depth of the network, and they reached top 5 error of 11.2% in the 2013 competition, and they reduced the error to 7.3% using an ensemble of these networks. Yeah, so one interesting idea here is to think about the memory usage of this network, and also the number of parameters. So yeah, the memory is more about the activation maps that result after every layer. So as you see, to store the activation maps, you need more memory for the first convolutional layer. So this is 3.2 megabytes, and you go down to 100 kilobytes, and for the fully connected layers you only need 496 floating point values. As for the number of parameters, so in the first convolutional layers you have a few filters. So having only 64 filters, you don't have so many parameters to learn, and also the input has only 3 channels. But then you observe a drastic increase in terms of the number of parameters when you go to the second layer. So this is because the input dimension is the number of activation maps is 64. So this increases gradually, and the largest number of parameters is when we switch from activation maps from the last convolutional layer to the fully connected layer. So here we have to connect every component in the activation map with a fully connected unit. So the total number of parameters is 100 million here. So you will notice that most of the parameters are in this layer, and in more recent architectures they observe that they can actually reduce, so you don't need so of course one approach is to take this pooling layer to flatten it, so transform this into a vector, and then add a fully connected layer after it. Or another approach with significantly fewer parameters is to add some global average pooling for each activation map in this layer. So when you do global average pooling, you will have 1 by 1 by 512 components. And so this is just like average pooling, only that the filter is equal to the size of the activation map. So when the filter has the same size of the activation map and you apply the filter only once, this is called global average pooling. So if you do this, then you have 512 by 4000 parameters. So you reduce the total number of parameters by 50. So instead of 100 million parameters, you will have about 2 million parameters here. So you will definitely reduce the number of parameters and the total number of calculations that you have to do. And you can obtain about the same performance, maybe 1% smaller. So it really also depends on the task, but you gain some efficiency if you add the global average pooling instead of flattening these activation maps. Okay, so yeah, the total memory is so for this sorry, so here is 3.2 million parameters, so million components. So actually the total number, the memory is 24 million times 4 bytes for floating point numbers, which is about 100 megabytes. So in order to process an image through this network, you need about 100 megabytes. So this is only for the forward pass. Remember that back propagation, the backward pass is about twice as the forward pass. So for the backward, you would need about 200 megabytes. And yeah, now depending on, for example, if you use a GPU with 4 gigabytes, so then you can use, for example, mini batches. So let's say 200 mega, so about maybe 20 examples in the mini batch, if I'm not wrong. Yeah, I think I'm not wrong. Yeah, so depending on the size of your GPU, you can already see that you cannot use mini batches that are so large. Okay, and yeah, the total number of parameters in VGG is about 140 million, so a lot of parameters to optimize. And as I previously observed, that most of the memory is required for the first convolutional layers, and most of the parameters are in the late fully connected layers. So now going on to a different architecture, Google Net. So in this architecture, they actually so the main idea in deep learning is to try to do end-to-end learning. So just to learn some parameters instead of trying to fixing them. And in Google Net, this is the winner of the ImageNet 2014 competition. They said, okay, why fix why to fix the spatial support of the filters, and instead of fixing I don't know, the path of in the network, they proposed an inception model that has alternative pathways. So from one layer to the next layer, you can reach through different pathways using 1x1 convolutions, using 2 convolutional layers with 1x1 and 3x3 convolutions. They also considered max pooling and 1x1 convolution. So they tried different configurations in order to reach different layers. So they introduced this inception model module in different locations in their architecture. So in the end, they have a network that's about, I think, 29 layer, if I don't mistake. So the main idea is that the network can choose to learn different pathways. So for example, in this location, it might learn strong weights for this pathway and this location for a different pathway and so on. And another question is that, okay, why to fix the depth of the network? We are not sure what is the best network depth to use. So instead of fixing the depth, they tried to use um, as many inception models as they could, and then they added some output layers with fully connected let's say output block with fully connected layers in different locations in the network. So there is an output block here, a different one here, and a different one here. So in the end, they take the output from all these levels in the network, and they combine them using an ensemble, like voting on all these outputs. So this is a more, in the end, they designed a more flexible architecture. They tried to reduce their engineering part and to let the network learn more things, like what is the right pathway, what is the right depth, and so on. Yeah, and they also reduced, so since they introduced these one-by-one convolutions in every pathway, they also reduced the number of parameters. So in the end, their network has about 5 million parameters, so it has significantly less parameters. Yeah, so they also remove the fully connected layers, so the once again the number of parameters is reduced also because of this. And actually the computation, so they use slightly more memory than AlexNet, so the computational time is only twice as big with respect to AlexNet. So yeah, in the end, they obtained a top 5 error rate of 6.7% on the ImageNet competition. And then the last network in our case study is ResNet. So this was the winner of the 2015 competition. So they had a 3.6 top 5 error rate. Then their main contribution was to add residual blocks. So the name of the network comes from residual blocks or residual connections. So they managed to train very deep neural networks with 152 layers. So they obtained first place in ImageNet classification and also good positions in ImageNet detection, localization, and so this is also ImageNet. And they also participated in the Microsoft Objects in Context challenge, and they also obtained second place there. Yeah, so on the ImageNet classification challenge, they reduced the top 5 error to 3.6%. So from the previous year, they managed to almost half the error rate from the previous year model. Yeah, and this also shows this graph from their slides, also shows the evolution of the top 5 error rates from 2012 to 2015. So yeah, this was the state of the art with engineered and handcrafted models, and in 2012 it is the first deep learning model. So this reduced the error by about 10%, and then another 10% we gained in 3 or 4 years with ResNet. Okay, so yeah, the main problem when you're trying to train so deep neural networks. So if you look at the results on a standard benchmark dataset like CIFAR-10, you see that 20-layer neural network attains small. So this is kind of the depth that you can reach with a classical convolutional architecture. Once you increase the number of layers, you see that the error increases both on training and on test. So this is a bit counterintuitive, because as you increase the number of layers, the model is supposed to be more complex, and it should be able to learn, it should be able to overfit to the training data. And they observed that this is not actually happening, and this is because the problem with vanishing and exploding gradients, as I explained before. So when they added their residual blocks, they observed that actually you can still increase the depth of the network, and you obtain better error rates on the training. So your model is more complex and can overfit to the training, but this is not only overfitting, the error also decreases on the validation. Okay, so yeah, this is just to give you an idea about the magnitude of their model. So this is AlexNet, VGG, and the number of layers in ResNet is much higher compared to these two networks. So in order to train ResNet, they needed about 2 or 3 weeks on a machine with 8 GPUs. But at running time, so the forward pass is faster than VGGNet, which is it had about 140 million parameters. Okay, so the network is the convolutional layers are inspired from Google Nets, so they use small filters with 3 by 3 and alternative pathways, but they also introduce these residual connections, also known as skip connections. So usually in a standard neural network, we have an input, you pass it through some convolutional layer, and you obtain this output. So in the residual network, they denoted these layers with a function f, and they add to this function f, they add the identity. So they just take the activation maps from this layer and they add them up here, and they obtain the output h, which corresponds to this output here. So in order to be able to introduce these skip connections, you need to make sure that here, when you apply your convolutional layers, the output and the input and the output have the same dimension. So when you add them component wise. So you add like just like two matrices here. So then these have to match in order to obtain a good output. Yeah, so this is the forward pass, and of course now the gradients can also backpropagate through these connections here. So the main benefit here is that yeah, you get backpropagation through these skip connections, so you avoid some computations in this layer, and this means that you can backpropagate the gradients faster through your network by just skipping some layers. Okay, and yeah, and this on the forward pass, this can also provide some alternative pathway. So if, for example, when you learn, the model can also decide that perhaps these layers are not useful, and just learn weights that are close to zero and just pass the information through the skip connection. So it's kind of a model that has a big depth, but you can also adjust the model automatically to a smaller depth. Okay, so yeah, I'm trying to watch also the time. So yeah, we have a question about, is there some sort of recurrent neural network architecture for the convolution part? Not sure what the question is about. So you mean to replace the convolutional layer with some recurrent network? Yeah, so there are recurrent networks. We're going to discuss about them later. And there are some also, for example, convolutional recurrent networks. They include in the recurrent cell the operations. Instead of simple operations, they use convolutional operations. Yeah, but it's not, I don't think it's common to replace. If you want to use a convolution, I think this is a very simple operation, and you don't want to replace it with something more complex unless you have a good reason to do so. So perhaps if you want to model some temporal information like videos, then you can have convolutions, and at some point you can add some recurrent network to model the temporal dimension. Okay, so going back to ResNet, yeah, they also train the network with SGD with momentum. They start with a learning rate of 0.1, and they decrease it by 10 when they reach plateaus. They use mini batches of 206 components, and they completely remove the dropout. Okay, and they also use this idea from the Google Net paper to optimize. So instead of using 3x3, two layers of 3x3, they use this residual block with 1x1 convolutions, one layer with 3x3 convolutions, and then another layer with 1x1 convolutions. Okay. Yeah, this is a table description of their neural architectures. So you can see here for their model where they replaced these convolutional blocks with those used in Google Net, and you can also see how many blocks of this kind they use. So they use 3 residual blocks with this configuration, then 8 residual blocks with this configuration, and so on. So yeah, in summary, the convolutional neural networks are a stack of convolutional pooling and fully connected layers. There is a trend towards smaller filters and deeper architecture. There is also a trend with architectures with alternating pathways. Yeah, also a trend to remove the fully connected layers and so on. So there are also more complex architectures that involve convolution. So for example, um, for image captioning and so on, you can, for example, apply a CNN on top of an image, some neural text embedding network to embed text into an embedding space, and then you try to match these two embeddings between the image and the text. So yeah, you can plug in CNNs in different architectures. Another um, idea is to train a single architecture for different tasks. So the same architecture can solve different tasks, and you can achieve some robustness in this direction. And yeah, there are even more complex architecture that can try to combine these convolutional blocks into various components. Yeah, but I think you really need not to do this randomly, but to have some motivation for doing it. Okay, so just this was the last slide. So I just finished in time. Let's see if there are still other questions.